So we are going to know what, why, and how of the topic functions. So what I'm going to cover today in this lecture is, firstly, we will have real life examples of functions that will form a base, because most of the times this information is missing while we are being taught the topic of functions in our schools or in colleges. We directly start from the mathematical expressions, but we rarely know the physical reason behind them, from where those mathematical expressions are appearing. So that is why I have included real life examples. And then I will give you the idea about variables, what is the meaning of variables, and then we will define function. And it is important to know the concept of domain and range for the functions. And then we will proceed towards mathematical examples of functions. First, we will have a look about 1-1-on-2 functions, which will help us to understand inverse of a function. Then I will be specifically talking about even and odd function, and then we will also talk about graph of even and odd function. And in between also I have included examples of functions graphically, because I believe the graphs are always a good way of visualizing what is happening mathematically. So let's first talk about real life examples. So the first example is the amount of money one gets as interest from savings in a bank is actually a function of time. The number of COVID-19 infections is dependent on the spreading or transmission rate of the virus, which further depends on the population density in that area or region. And the speed of an object thrown vertically upwards is dependent on its initial speed. So these are the three examples. So if you talk about the very first example, so the very first example, it's very easy to understand that you want to know that how much money you will get as interest by keeping your money in the bank account, which is a savings bank account. So it obviously is a function of time, because for more time you keep the money in the bank, the more interest you will be getting. The rate is going to be constant, but over the years, the amount of interest is going to increase. The amount of money will keep on increasing in the bank because interest gets added up. So it's a function of time. The number of COVID-19 infections is dependent on spreading or transmission rate of virus. So this is the example which I found relevant in today's scenario, because everywhere we are talking about COVID-19. So we know everyone is interested that how the infections are going to rise, whether they are going to stop rising one day, or we will have a day in future when there will be absolute no COVID-19 infection reported globally around the world. So because of those curiosity, we are interested in doing the analysis for COVID-19. So looking at it as a function, it is dependent on how the virus is spreading, at what rate it is spreading itself, and which further is a function of depending upon the population density of that area. Because higher the population density in a particular area, it's highly likely the virus will transmit itself at a faster pace. The third example is also very easy to understand. When you throw an object vertically upwards, so its speed with which it is going to move is depending upon its initial speed, with what speed you initially have thrown it upwards. So it's clearly very easy to understand. Basic examples from the physics. So you can have plenty of examples and you can create even your own examples to understand the functions. But here I have tried to include examples from different areas so that you get an idea that these kind of examples exist everywhere. So you can have the real life examples of functions everywhere around you. And now we will be talking about dependent and independent variable. Because you see, the terms which I have just used in explaining the real life example tells you that I'm always telling one quantity is depending on the other. So this introduces this notion. When one phenomena or process depends on some other quantity, then we have two kinds of quantities or variables. The first one we are going to talk about is independent variable. So the quantity which is changing on its own usually falls into the category of independent variables. For example, space and time. And what is dependent variable? The other variable which is changing with respect to the independent variable is called as dependent variable. For example, the COVID-19 active cases is dependent on the time or population density. So the time in that case is acting as independent variable because we do not have a control over the independent variable. It is something which is changing on its own. So usually space and time are coming into this category, and the rest of the things, whichever are our unknowns or whichever are our variables, they are changing their values or they are depending upon the independent variables. So they fall under the category of dependent variables. So in this example, if I talk about the number of COVID-19 active cases is changing with respect to time because every day there is a different number. So it's changing with respect to time. So time is independent quantity there, and the COVID-19 cases is the dependent quantity there. Now, why we need to talk about quantities or variables? Because you have got our aim now. You want to understand these real life processes from a mathematical point of view. So to understand the things mathematically, you need to have variables. You need to have notations for them. So that's why we need these terms, dependent and independent variables. And now you are clear about dependent and independent variables, we can talk about the definition of a function. It is also known as a mapping. So in many books or many authors will use the word function and mapping interchangeably. So let's look at the definition. A function is a relationship between dependent and independent variables, right? So now you know the meaning of dependent variable and independent variables. So there's a mathematical relationship between dependent and independent variable. So that is going to be known as a function. And what is the particular thing about it? It maps to each element of independent variable to a unique element of dependent variable. So you have x is the usual notation for independent variable and y is the usual notation for dependent variable. So this is how we denote a function. Y is equal to fx, and sometimes y is equal to f of t, where t usually stands for time. So if these are the values taken up by independent variable, x1, x2, x3, and these are the values taken by corresponding functions at x1, at x2, and x3. So again, you can take the example of COVID-19. Say x1, x2, x3 denotes the time. On the very first day, you had some particular number of infections. So that is fx1. On second day, that is x2 is equal to 2, you have the number of infections increased. So that is a different number. So that means corresponding to every day, you get a different number. So this is how there is a functional relationship going on between x and y. So this is the meaning of a function or a mapping. And now let's look at the word unique. What do you mean by unique? Unique means that x1 can be mapped to only one element, y1, which we call fx1. This cannot be possible. This is not a function because if x1 you map to fx1 as well as x1 you map to some other value, y1 is not same as y2, then this cannot fall into the category of a function. That is the meaning of the word unique, that x should be mapped to a unique y value. So this is not a function. However, you can have this picture that two different elements of independent variables can have the same value of dependent variable. So the number of infections can be same on the first and the 10th day, right? It can be same. So corresponding to x1 is equal to 1, it can be the same value as we have for x1, x2 is equal to 10. So this can happen. This is okay for being a function, but this is not okay. So this is the fundamental definition of a function. This is how we define a function. And now we have introduced x and fx or y. So we can talk about domain and range. So the set containing independent variables is called domain of function, and the set containing dependent variables is called range of function. And how we denote this? So domain is denoted by df, range by rf for the function y is equal to fx. So you symbolically draw it like this. You have a domain, you have a range, and from domain to range you have a function. x1, x2, x3 have their images y1, y2. So domain and range, both of them can be finite or infinite sets in general, because we are talking about set. So these can be set of integers, these can be set of natural numbers, real numbers, rational numbers, complex numbers. So they can be, the elements can be anything. So as a set, they can be a finite or infinite set. So now you understand what is the meaning of function, domain, and range. We are ready to look at the mathematical examples of the function. So although again, you can have infinitely many examples created for the functions, I have tried to include few important examples. So the first one is constant function. Constant function is a function which maps every element of the domain to a single constant value in the range. For example, if you define a function from z to z, so z is the basically notation for integers, the set of integers. If you define it like fx is equal to 0 for all x belonging to the integers, so what you have done basically, whatever x be, the final answer is going to be 0. So all integers are having their image as 0. So it can be other than 0, something like it can be 1, -1, -3, +5, whatever it can be, but it has to be something in the set of integers. So if you define a function like this, fx is equal to a constant, then we say that is a constant function. So this is a trivial kind of an example. This is a trivial function which you will see in many of the future applications, because there are some things which do not change at all. Whatever the domain variable is changing, their value remains same, which is the constant value. So that gives us idea about constant function. And then you can talk about the next kind of function, which is identity function. Identity function maps every element of the domain to itself. For example, if you define function from R to R, so this R is a set of reals. This is a mathematical notation for reals. It is defined by fx is equal to x, because you are mapping every element to itself. Like 1 will be mapped to 1, square root 3 will be mapped to square root 3, pi will be mapped to pi. So be it any real number, its image is going to be the same number itself. So this function also comes under an important category of functions and known as the identity function. So these are the standard examples. Next example we are going to include is algebraic function. So let me give you the definition. So for example, you have this kind of functions: y is equal to x square, square root x, x cube, mod x, x raised to power 1 by 3, y is equal to mx, where m can have any integral value, right? So these are algebraic functions. Basically, you can see the relationship between the variable is algebraic. Now, what are algebraic relationships, or what are the operations that fall under the category of algebraic is you can multiply, you can add, you can do raised to the power, you can subtract, you can divide, take modulus, and so on. You can have fractional powers also. So these are all functions because x is being multiplied with itself here. So this gives you x square. X is being raised to power 1 by 3. So this also comes in the category of algebraic function. So you operate x with itself and do similar operations with it. Whatever function kind you get, that is algebraic function. So these are few examples. You can have again infinitely many. And then you have transcendental functions. Y is equal to log x, e raised to power x. And then you have trigonometric functions. Trigonometric, we are already familiar with sine x, cos x, tangent x, then cotangent x, cosecant x, and secant x. We have basically 6 basic trigonometric functions and their operations with each other. We can do sine inverse, we can do cos square, we can do tangent into secant. So they are multiplied among themselves, divided among themselves. So whatever they will be, they will fall under the category of trigonometric functions. And what about transcendental functions? Yeah, so transcendental function is basically the functions which are not coming in the category of algebraic functions, right? So this is different than algebraic, as you can see. So you have the exponential function coming up and the logarithmic function coming up. I would say there is a more profound definition, more deeper definition of transcendental function, but at this level, because we are just going to talk at a very basic level, not at intermediate or a higher level. So I'm not going to talk more about transcendental function here, as that might confuse you if you're not familiar with the some advanced concept. So here for the definition is this much only, that you can have the examples of the functions which fall into the category of transcendental and all. And lastly, I would say it does not matter whether you name the function or not, or whether you know in which category it falls. All what matters is the what you do with that function, okay? How you differentiate it, you find its integral, or you find the limit of the function, you see whether it is continuous or not. So all those coming up concepts you will see will be used and taught in a way that you will feel there is actually no need to know or remember the name of the category of the function, in which category your function is lying, right? So it's not going to matter at all. So that's about few basic mathematical examples of the functions. And now I'll be talking about another very popular term which is used very frequently in this concept. What do you mean by one or onto functions? So one is if no two elements of the domain are mapped to a single element in the range, then the function is said to be 1. For example, y is equal to x, identity function. So this is like domain, this is the range of this. So you can see 1 is mapped to 1, 2 is mapped to 2. So this is a 1 map. So if you read the definition again, no two elements of the domain are mapped to a single element. That means each element in the domain is going to have its unique image. And obviously, you cannot have the situation like this. 2 cannot be mapped to 1. So no two different elements of the domain are being mapped to a single element. So if that is the case for a function, that function is said to be 1. And this is one example of a 1 map. There are plenty of others. And then you have the definition of onto. So if every element of, let me define it like this, if every element of range has pre-image in the domain, then map is said to be onto, right? So for example, if I give you a map, y is equal to fx is equal to 1. So if it's a constant function and I define it on the set 1 to n, then this is not an onto function. Because what you are doing, every single element is being mapped to 1, and you see there are rest of the elements other than 1 here in the range, other than 1 here, there will be 2, there will be 3, and there will be 4. So those elements are not having any pre-image in the domain. Therefore, this is not an onto map. So if every element of the range has its pre-image, then the map is said to be onto. That means there cannot be any extra elements here which do not have any pre-image. Those kind of functions are onto functions. And this is the again a way to understand which is not allowed in 1-1 map. This is something I have already explained. So this is a conceptual meaning of 1-1 and onto. And then there are mathematical ways actually of checking. How do you check whether a given function is 1-1 or a given function is onto? So right now I'm not going into details of that. So just by applying the definition and verifying, you can say which function is 1-1 and which is onto. Moving ahead to the inverse of a function. So let's first know that 1-1 map is also called as injective map. Onto map is also known as surjective. These are the other names. And a map which is both 1-1 and onto is called bijective. If you have heard this term before, so that is well and good. Otherwise, this is the meaning of a bijective map. It should be both 1-1 and onto. So when do we say a function inverse exists? Means we are talking about, like you have seen the functions as sine inverse x or tangent inverse x. So when you can talk about a function inverse is existing, for that a function has to be first bijective. So this is what in the meaning of invertible function is, that for a function to be invertible, it should be bijective, both 1-1 and onto. And then how do you define the inverse of a function? So if y is equal to fx is a bijective function, then x is equal to f inverse y is its inverse. F is from a to b, g will be from b to a, such that fx is equal to y, then g is said to be f inverse. So that means it is simply, what we have to do here is, your original function is y is equal to fx. So you have to express x in terms of y. So you have to use this expression to reach to another expression such that x can be written as in terms of y. So that function will be f inverse, or you can denote it with altogether new symbol. Let's call it g. But g is essentially as a function same as f inverse. So firstly, we talked about when it is possible for a function to be invertible. So it should be bijective. So once we know it is bijective, then we can define the inverse of a function in this way. So let's look at the examples. So the first example is the identity function. So the inverse is x is equal to y. So I have told you how to find the inverse. So simply you just from the given expression express x in terms of y. So for this, the same function is its own inverse. This is also identity function. So the inverse of identity function is the identity function itself. And then you talk about y is equal to x square. So if I define y is equal to x square defined on this domain. So this is the domain I have chosen for positive y is equal to x square, positive reals including 0. Otherwise, the domain of this function is all reals. If you talk about the domain of this function, so it is defined for every positive real values for R. X can have any real value. But I have particularly chosen here positive reals including the 0, because it is over this domain, this function is bijective and therefore invertible. So that means to talk about the inverse of this function, you need to restrict its domain to non-negative reals. Positive and 0 means non-negative. And then inverse of this function is this, because when you try to find x in terms of y from this expression, then you get x is equal to square root of y, and square root of any real number is always positive. Obviously, y is already positive, but the square root of it is also going to be a positive quantity. So that gives us idea that x has to be positive. That is why the domain is positive reals, right? Because here I've explained, if we take domain to be all reals, which is the original domain of the function, then this function is not 1, 1, because it is mapping 2 to 4. It is also mapping -2 to 4, as you can see from the definition of y is equal to x square. So since it is not 1, 1, therefore it is not invertible over its whole domain. It is invertible only on this domain. And then we have the third example, y is equal to 2x. Its domain is also all reals. But if I take the domain to be integers, if I define this particular function to be on integers and I map it like this way, fx is equal to 2x, then this is not invertible because f is not on 2. It will be 1, 1, you can check, because it's like 1 will be mapped to 2. 2 will be mapped to 4 because you have to multiply by 2, right? Y is equal to 2x. So it will be 1, 1. No two single elements will be mapped to the same element in the range, but it will be not onto. Now you have to think about it. Why it will not be onto? Because there will be some extra integers left. Like in the set of integers, you not only have even integers, you also have odd integers. As you can see, the range set will be containing only even integers 2, 4, 6, 8. So what about the odd integers 1, 3, 5? They will not have any pre-image, and hence this map is not going to be onto. Therefore, this map is not invertible. So this is the example where I have shown you how to compute the inverse of a function, and how do you see about it whether a given function is invertible or not. So if it is not invertible, obviously we cannot talk about its inverse. And now let's talk about graph of a function. As I told you earlier, that graph is the best way to visualize a function. So let's look at what is the meaning of it. How do you obtain the graph? It is obtained by drawing the points in Cartesian plane, which is the xy plane, whose coordinates are input or output of the function, which is, say, y is equal to fx. For example, you have x-axis, y-axis. So this is our Cartesian xy plane. And these are, say, points obtained from a function. So when we join those points and we get graph of that particular function. Say y is equal to fx. This is the circle. So this is a graph of a circle, which is a graph of equation of the circle. But it cannot be the graph of a function, because you see, for one single value of x, you can have two different f values, which is against the definition of the function. One value of x cannot be mapped to more than one values of fx. It should have a unique image. So that is why this is graph, but this is not the graph of a function. This is the graph of a curve. So this point I just added because most of the students get confused between how do you differentiate between graph of a function and graph of a curve or equation. So for a graph of a function, it cannot be like this graph of a circle. And now we look at some particular examples of graphs. So the first example is constant function. Y is equal to c, where c is positive. It will be a horizontal line. And c negative, again, it will be a horizontal line. Y is equal to x is a straight line passing through origin. Y is equal to mx is also again a straight line passing through origin with the slope m. Y is equal to x was having slope 1. Y is equal to mx is having slope m. And mod x, this is a graph of absolute value of the function, because it has to take positive values whether x is negative or whether x is positive. So this is how mod x is defined. And then y is equal to x square is having this graph vertically upward parabola, and y is equal to x cube is having this graph. So these are again few examples, but if you want to really learn about how to graph a given function, so it's a whole detailed different area which requires detailed knowledge about many other aspects of the function, which we are not introduced yet, because it needs knowledge of the tangents, it needs the knowledge of slopes. So for that we need to introduce the concepts of limit and the derivative. So that is why how to draw a graph, that is not included in this video lecture. But here I've just given you the examples of standard functions which are known to everybody and they can be used directly. They have their standard graphs. And now we are going to talk about even or odd function, because this is also a very important terminology one should know about whenever you're talking about functions. So let's talk about what is an even function. So if fx is same as f of minus x, that means the function is having same values, whether x is positive or negative with the same magnitude, then function is an even. For example, x square, x raised to power 4, and you can check these functions are even functions. Y is equal to mod x is also an even function because mod of x is same as mod of minus x. And what is an odd function? If f of x is negative of f of minus x, then that function is said to be odd function. For example, y is equal to x cube, y is equal to x. So these are the examples, and I have shown here how they are satisfying the definition of being an odd function. Y is equal to sine x is an odd function because sine of minus x is minus of sine x. On the other hand, cosine x is an even function, the trigonometric function if you talk about. So this is how you have to check. These are the checking conditions. Whenever you need to check a function is even or odd, so you need to know these conditions. Now, here a question can come to our mind, why we are interested to know about even or odd functions, because this concept helps us to simplify many things about the function. As I'll show you that how do the graphs of even or odd function look like. So from there you can draw an inference that what is the benefit of knowing a function to be even or odd. And remark is here that there are functions which are neither even nor odd. Okay, so it's not like integers, every integer has to be either even or odd, but there are functions which are neither even nor odd. So if you look at the graph of even functions, so with these examples, if y is equal to x square, this is how the graph is going to look like. Mod x, this is the graph of mod x, and cosine x. Cosine x is an even function. This is the graph of cosine x. What is the common about these? That symmetry with respect to y-axis there. So if you look at all three graphs one by one, so you see whatever you have drawn on the right side of y-axis, exactly its mirror image is drawn on the left of the y-axis. So there is a symmetry with respect to y-axis. So this is an important property about the even function which you can use while graphing. So that means even if you draw the graph for one side of the domain, so you draw only for positive values and then just take its mirror image or reflection in the y-axis, you will get the complete graph of the function. So that is the benefit of knowing if the function is even. And then look at the odd function graph. So in odd function, y is equal to x. This is the graph. Y is equal to sine x. We have, this is the graph of y is equal to sine x, and y is equal to x cube. So what is a common here? So there is a symmetry with respect to origin. That means you can say whatever you draw in first quadrant, the same thing you draw in the third quadrant. So there is a reflection has to be taken with respect to the origin. So here also, if you just know the function values in first and second quadrant, you can reflect that. So the first quadrant will be reflected in third, the second quadrant value will be reflected in fourth quadrant. If there is nothing in second, obviously, so nothing is going to be there in fourth quadrant. So that is the benefit of knowing whether a function is odd. So you have that information about that function. So its graph is a reflection with respect to the origin. So that's all about the basics of functions. I have included few examples. The reason being for that is whatever the concepts are going to proceed now, limits, continuity, differentiability. So we will have a variety of examples of functions there as well. So in the next part, we are going to talk about another important concept, which is limits of the functions. So thank you very much.